Introduction. Friends, we are well familiar with the idea of summing finitely many numbers or quantities, but today we are going to learn the concept of infinite sums, which is needed quite often in mathematics. The idea of infinite sums is related to the concept of convergent and divergent sequences, and so we shall begin with the formal definition of sequence and its limit. Definition: sequence. An infinite sequence of real numbers is a function f with domain as set of natural numbers n and codomain as set of real numbers r. Although by definition sequence is a function f on the set n, which usually it is written as xn, n runs from 1 to infinity, or as x1, x2, x3 and so on, where xn is the value of this function at the point n in set of naturals, that is xn is f of n. Thus, intuitively a sequence is simply a list of numbers. Our major interest here is whether a given sequence of numbers xn approaches a fixed number as n tends to infinity. Let us make this point more precise by defining the limit of a sequence. Definition: limit of a sequence. Let xn be a sequence of real numbers and L be any real number. We say that the sequence xn has limit L or it converges to L, and we write limit of xn as n goes to infinity equal to L, or xn goes to L as n goes to infinity if for every epsilon greater than 0 there exists a positive integer n naught such that mod xn minus L is less than epsilon for all n greater than equal to n naught. From the definition, we understand that a sequence xn has limit L if xn is sufficiently close to L for all n sufficiently large. Also, it is a very simple task to show that if the limit of a sequence exists, then it is unique. If a sequence has the limit, then it is called a convergent sequence. Otherwise, it is termed as a divergent sequence. Note that the simplest example of a convergent sequence is a constant sequence, that is xn equal to alpha for all n. It is obvious that whether a given sequence xn is convergent or divergent depends purely on the behavior of xn for large values of n, and so the first 1000 or the first billion terms of the sequence are irrelevant when we are discussing issues related to the convergence or divergence of the sequences. Properties of limit. Let xn and yn be convergent sequences. Then number 1, limit of xn plus or minus yn as n tends to infinity is equal to limit of xn plus or minus limit of yn. 2, limit of xn into yn as n tends to infinity is same as limit of xn multiplied to limit of yn. 3, limit of xn over yn as n tends to infinity is same as limit of xn divided by limit of yn, provided limit of yn is not 0. 4, limit of alpha times xn as n tends to infinity is same as alpha multiplied to the limit of xn for every real alpha. We now discuss few theorems which are helpful in understanding the concept of convergent sequences. For this, we require some definitions. Definition: bounded sequence. A sequence xn of real numbers is said to be bounded if there exists a real number m such that mod xn is less than or equal to capital M for all n. Definition: increasing or decreasing sequences. let x n be a sequence of real numbers, then it is said to be increasing if x n is less than equal to x n plus 1 for all n. On the other hand, if x n is greater than equal to x n plus 1 for all n, then the sequence is said to be decreasing. A sequence which is either increasing or decreasing is also called a monotonic sequence. Theorem: every convergent sequence is bounded. Theorem: every monotonic bounded sequence is convergent. Theorem: if x n converges to L as n goes to infinity, then for every epsilon greater than 0, there exists a positive integer n naught such that modulus value of x n minus x m is less than epsilon for all n comma m greater than equal to n naught. Let us now take a simple example. Example: find the limit of the sequence 1, 1 by 4, 1 by n and so on. Solution: let x n be equal to 1 over n square. Clearly, this sequence x n is decreasing and bounded, and so it is convergent. We see that as n gets larger and larger, x n gets closer and closer to 0. Hence, we expect the limit of this sequence to be 0. To prove this, given a positive number epsilon, we want to show that there exists a positive integer n naught such that 1 over n square is less than epsilon for all n greater than equal to n naught. But it is easy to see here that if we choose n naught to be any positive integer greater than 1 over square root of epsilon, then our requirement is fulfilled, and so we have limit of 1 over n square to be 0. About divergent sequences, consider the sequences x n equal to minus 1 raised to n and y n equal to n square. It is clear that none of these two sequences approach any finite number or limit, no matter how far we go down the sequence, and so these two sequences are divergent sequences. Although x n is equal to minus 1 raised to n and y n equal to n square, both are divergent sequences, there is a difference in the way they diverge. Note that the sequence y n does not converge to a finite number because its terms are approaching infinity as n tends to infinity, whereas the sequence x n does not converge because its terms are bouncing around indefinitely and so cannot settle to a specific value. Such divergent sequences are also known as oscillatory sequences. Sequences with limit as plus infinity or minus infinity. We have given a precise meaning of the notation limit x n equal to L when L is a finite number, but sometimes it is equally important to understand the meaning of limit of x n equal to plus infinity or limit of x n equal to minus infinity. Definition: for a sequence x n, if for every m greater than 0, there exists a positive integer n naught such that x n is greater than m for all n greater than equal to n naught, then we say that x n tends to positive infinity and write limit of x n equal to plus infinity. On the other hand, if for every m less than 0, there exists a positive integer n naught such that x n is less than m for all n greater than equal to n naught, then we say that x n tends to negative infinity and write limit of x n to be equal to minus infinity. Note that if x n is a sequence of non-zero numbers which tends to positive or negative infinity, then limit of 1 over x n is 0. We now record some useful results. Theorem: let R be any real number and P greater than 0. 1. Limit of n raised to P as n tends to infinity is equal to infinity. 2. If mod R is greater than 1, then limit of mod R raised to n as n tends to infinity is equal to infinity. 3. If mod R is less than 1, then limit of R raised to n as n tends to infinity is equal to 0. 4. Limit of nth root of P as n tends to infinity is equal to 1. 5. Limit of nth root of n as n tends to infinity is equal to 1. And 6. Limit of n raised to R over nth power of 1 plus P as n tends to infinity is. Since we are often encountering with finding the limit of quotient of polynomials Pn over Qn, we take an example to understand it. Example: determine limit of 2n cube plus n minus 1 over n cube plus n square plus 6. Solution: note that 2n cube plus n minus 1 over n cube plus n square plus 6 is equal to n cube times 2 plus 1 over n square minus 1 over n cube divided by n cube into 1 plus 1 by n plus 6 by n cube, and this is equal to 2 plus 1 by n square minus 1 by n cube divided by 1 plus 1 by n plus 6 by n cube. Using the properties of limit, it follows that the required limit is 2 over 1, which is equal to 2. The technique used in this example can be used to derive a general result about the limit of a quotient of any two polynomials. Theorem: if Px and Qx are polynomials with leading coefficients as L greater than 0 and m greater than 0 respectively, then A limit of Pn over Qn will be equal to L over m if Px and Qx are of same degree. B limit of Pn over Qn will be 0 if degree of Qx exceeds that of Px. C limit of Pn over Qn will be equal to infinity if degree of Px exceeds that of Qx. In mathematics as well as economics, the sequence 1 plus 1 by n whole raised to n has a distinguished importance, and hence we need to know its behavior as n tends to infinity. Since this sequence is increasing and bounded, it is convergent and its limit is defined to be the number e. It is an irrational number whose approximate value is 2.71828. In mathematics, there are many equivalent definitions of e, but here we would like to see an economic interpretation of this number e. Note that 1 plus 1 by n whole raised to n is the year and amount to the principal amount of 1 unit if it is assumed to grow at 100% per annum and if the interest is compounded n times in a year at regular intervals. With this interpretation, E is simply the year and amount to the principal amount of 1 unit if it is assumed to grow at 100% per annum and if the interest is compounded continuously. In economics, we often deal with exponential, logarithmic and polynomial functions, and on certain occasions it is important to compare the growth of these functions with each other. The following result highlights this matter. Theorem: let t be any positive number, then 1 limit of log n over n power of 1 plus t is equal to 0. 2 limit of Pn over n power of 1 plus t is 0, where Pn is a polynomial in n. 3 limit of log n over Pn is 0 where P n is a polynomial in n. It can be inferred from these three results that the growth of the exponential function is much faster as compared to the growth of logarithmic or polynomial functions. Further, the growth of the polynomial function is faster than that of logarithmic function. Series of numbers. Given a sequence x n of real numbers, we associate with it the infinite sum or series denoted by sigma x n, where n runs from 1 to infinity. Our goal here is to assign a precise meaning to the symbol sigma x n, where n runs from 1 to infinity. Intuitively, we understand that sigma x n means the value of the finite sum sigma x n when n runs from 1 to k for larger and larger values of k, and this intuition leads to the following idea of convergence of series. About convergent and divergent series. Given a sequence x n, consider the finite sums of the type s k, which is equal to sigma x n, where n runs from 1 to k for k belongs to set of naturals. Then we say that the series sigma x n converges to a number L, and write sigma x n is equal to L if the sequence s k converges to L, s k tends to infinity. If this does not happen, then we say that the series is divergent and the symbol sigma x n has no meaning. However, if limit of s k as k goes to infinity is positive or negative infinity, then we say that the series sigma x n diverges to infinity, and write sigma x n equal to infinity or sigma x n equal to minus infinity respectively. The sequence x k is often called the sequence of partial sums of the series sigma x n. We have earlier made a point that the convergence or divergence of any sequence is not affected by the first million or the first billion terms of the sequence. So, this applies to the sequence s k, and consequently the convergence or divergence of any series is not affected by the first million or first billion terms of the series. Notice that if the series sigma x n converges to a number L, then limit of x k as k goes to infinity is same as limit of s k minus s sub k minus 1 as k goes to infinity, which will be equal to L minus L, and this is 0. Thus, for the series sigma x n, if limit of x k as k goes to infinity is not 0, then we can immediately conclude that the series is not convergent. On the other hand, if limit of x k as k goes to infinity is 0, then the series may not be necessarily convergent. For this, we may consider the example of the harmonic series sigma 1 over n. It can be worked out that if s k is equal to sigma 1 over n, where n runs from 1 to k, then s sub 2 raised to k will be greater than equal to k plus 2 divided by 2, and so the sequence s k turns out to be unbounded. This results into s k being divergent, and hence the series sigma 1 over n is not convergent. In fact, we have sigma 1 over n equal to infinity. This can also be interpreted as, given any positive number m, we can find a positive integer k such that sigma 1 over n, where n runs from 1 to k, is greater than m. Basic properties of the series. 1. If the series sigma x n and the series sigma y n are convergent, then the series sigma x n plus or minus y n is convergent, and sigma x n plus or minus y n is equal to sigma x n plus or minus sigma y n. 2. If the series sigma x n converges and alpha belongs to set of reals R, then the series sigma alpha x n converges and sigma alpha xn is alpha times sigma xn. Geometric series, let R be a real number, then the series sigma r raised to n as n runs from 1 to infinity is equal to r plus r square plus r cube plus so on is called the geometric series. The test for the convergence of geometric series is very simple. If mod r is less than 1, then it is convergent, and further sigma r raised to n will be equal to r over 1 minus r, whereas if mod r is greater than equal to 1, then it is divergent. Such types of series occur when we think about the decimal expansions of some rational numbers. For instance, if we consider the number 1 by 3, its decimal expansion is 0.3333 and so on, which may be written as 3 times 1 over 10 plus 1 over 10 square plus 1 over 10 cube and so on, which is equal to 3 times 1 over 10 divided by 1 minus 1 over 10, which will be equal to 3 by 9, or this is same as 1 by 3. Telescoping series. A telescoping series is a series whose partial sums eventually have fixed number of terms after cancellation. One popular example of such a series is sigma 1 over n into n plus 1, or more generally sigma 1 over n plus l into n plus p, where l is less than p. Here we may write sigma 1 over n plus l into n plus p is equal to 1 over p minus l times sigma 1 over n plus l minus 1 over n plus p. It is very easy to determine the convergence of the series which are geometric or telescoping, but this is not always the case for arbitrary series. So, we now introduce some of the tests which help us in determining the convergence or divergence of a given series. Comparison test. 1. If mod xn is less than equal to yn for n greater than equal to n naught, and if sigma yn converges, then sigma xn converges. 2. If xn is greater than equal to yn, which is greater than equal to 0 for n greater than equal to n naught, and if sigma yn diverges, then sigma xn diverges. The comparison test is very useful, especially if we are familiar with certain convergent or divergent series of non-negative numbers. Cauchy's condensation test. Let xn be a decreasing sequence of non-negative terms. Then the series sigma xn converges if and only if the series sigma 2 raised to n x sub 2 raised to n converges. In view of the geometric series test, the Cauchy's condensation test now immediately gives some nice results. Results: 1. The series sigma 1 over n raised to p converges if p is greater than 1 and diverges if p is greater than 0 and less than equal to 1. 2. The series sigma 1 over n into p power of log n converges if p is greater than 1 and diverges if p is greater than 0 and less than equal to 1. Using these results, we now work out an example based on the comparison test. Example: determine the convergence or divergence of the series sigma sin n square divided by n square and sigma log n divided by n. Solution: let xn be equal to sin n square divided by n square and yn be equal to 1 divided by n square. Since mod xn is less than equal to yn for all n greater than equal to 1, and because we know that sigma 1 over n square is a convergent series, it follows from the comparison test that the series sigma sin n square over n square converges. For the second series, we take xn equal to log n divided by n and yn equal to 1 divided by n. Note that xn is greater than equal to yn greater than equal to 0 for large values of n, and further the harmonic series sigma 1 over n is divergent. So, the comparison test implies that the series sigma log n over n diverges. The alternating series test. Let x n be a decreasing sequence of non-negative terms, then the series sigma minus 1 raised to n into x n converges if limit of x n is 0. Recall that sigma 1 over n raised to p is divergent for p greater than 0 and less than equal to 1, follows from the Cauchy condensation test. But if we alternate the sign of the terms of this series, then due to the alternating series test, we deduce that sigma minus 1 raised to n upon n raised to p is convergent for any p greater than 0. This result indicates that sometimes the convergence of a series is greatly influenced by the cancellations involved in the series. The comparison test suggests that a series converges if the rate of convergence of its terms to 0 is high enough, but it is not always possible to judge this rate of convergence, and in such scenarios sometimes the ratio and the root tests are useful. So, we discuss this test one by one. The ratio test. For the series sigma x n, suppose that limit of mod x n plus 1 over x n is L. Then number 1, sigma x n converges if L is less than 1. Number 2, sigma x n diverges if L is greater than 1, and number 3, the test is inconclusive if L is equal to 1. The ratio test can be applied to conclude that the series sigma x raised to n over n factorial converges for every real x. Further, it can also be used to establish that the series sigma n factorial upon n raised to n converges. The ratio test can be applied to conclude that the series sigma x raised to n upon n factorial converges for every real x. Further, it can also be used to establish that the series sigma n factorial upon n raised to n converges. The ratio test is mainly used when the general term of the series involve factorials. Some of the series where this test is inconclusive are sigma 1 over n raised to p and sigma n square upon n square plus 2n. The root test. For the series sigma x n, suppose that limit of mod x n to the power 1 by n is L. Then number 1, sigma x n converges if L is less than 1. Number 2, sigma x n diverges if L is greater than 1. And number 3, the test is inconclusive if L is equal to 1. Here we are assessing the value of the nth root, and so the root test is mainly used when the general term of the series has powers. The following rules for non-exponentials are also sometimes useful while applying the root test. Number 1, limit of nth root of c is 1 for every positive constant c. Number 2, limit of nth root of log n is 1. Number 3, limit of nth root of n to the power p is 1 for every positive exponent p. Number 4, limit of nth root of n factorial is infinity. Example, test the convergence or divergence of the series sigma minus 1 raised to n into n square divided by nth power of 1 plus n and sigma 2 raised to n square divided by n raised to n. Solution. Let x n be equal to minus 1 raised to n times n square divided by nth power of 1 plus n. Then limit of nth root of mod x n will be same as limit of n raised to 1 by n whole to the power 2 divided by 1 plus n, and this is same as limit of 1 over 1 plus n, which is 0, which is less than 1. Hence, by the root test, the series sigma minus 1 raised to n into n square divided by 1 plus n to the power n is convergent. For the second series, we observe that limit of nth root of mod x n is same as limit of 2 raised to n divided by n, which is equal to infinity, and hence the series sigma 2 raised to n square divided by n raised to n is divergent. Summary: we give a formal definition of a sequence and its limit and understand the concepts related to the convergence and divergence of sequences. Later, we use the concept of a limit of a sequence to define the infinite sums or series. The problem of determining whether a given series is convergent or divergent is not always easy, and for this various tests are introduced and studied in this module. Thank you.